free fall, or the acceleration due to gravity. What happens when you drop an object? Please click over here for an MIT video about a falling object. There are 4 observations that can be made about that video. Initial velocity, your change in position, your change in velocity, and then the acceleration. Is the acceleration due to gravity? And again, gravity is what was pulling the ball down, and it's also what's going to be pulling a hammer down here in the Apollo 15 video. Is it the same for all objects regardless of mass? So first click here, this is a wonderful video, and then click over here for the world's largest vacuum chamber video. Here's our definition of free fall. Any object that falls only under the influence of gravity is said to be in free fall. Now, objects in free fall are assumed not to be affected by air resistance. We'll do those type of problems when you get further on in physics, but for now, we'll assume no air resistance, which is why the Apollo 15 video was so cool, because there's no air on the moon. These objects accelerate downward, at least on the planet Earth, at 9.8 meters per second squared. We'll approximate that as 10 meters per second squared to make the math easier. The acceleration due to gravity is very special, so we have a special letter for it. We'll call it little g, g for gravity. So the acceleration due to gravity is a negative g, negative 10 meters per second squared. The negative sign indicates that the acceleration is downward. But when you see just g written like this, that's always a positive 10 meters per second squared. That's a magnitude. When you want the direction on it, the direction of the acceleration, that would then be a equals minus g, which would be our minus 10 meters per second squared. Try filling in the velocity and acceleration columns for this table, for this green sphere over here, that is in free fall. So only gravity is acting on it. Here's a hint. Use the first kinematics equation for the velocity column. And let's go ahead, might as well write that here. So it's Vf is equal to V initial plus At. Now be careful about the signs and assume this direction here is negative. So please fill this in, pause the video if needed, and come on back to the next slide. Here's our equation, which I did show you on the last slide. Now it's very important to use this equation properly. You see it's all positive signs there. That's true, that's how it works. But what is our acceleration going to be? Acceleration at everywhere in this process will be due to gravity, right? Just because you drop a ball, it doesn't mean it leaves the Earth's gravitational field. So the acceleration will be a constant negative g, negative 10 meters per second squared, always pulling the object down. So the right-hand column here was pretty straightforward. You just put in minus 10. Notice we didn't put the units in the individual spaces. Why? Because the title here has the units right in it, so you don't have to put them in each individual cube here. Even when the object isn't moving, that acceleration kicks in as soon as you let it go, so we keep it up there at negative 10. So at time 0, you're not moving. You drop it. After 1 second, we look at this equation here. Vf is equal to V initial, and V initial is 0. Probably should have mentioned that earlier, but there it is. So you have 0 minus 1 times 10. Here it is. Negative 10 meters per second. See how the negative took care of itself? Right, we've got the negative 10 there times a positive time. After 2 seconds, we're doing negative 20 meters per second. 3 seconds, negative 30, and so on. Now, meters per second may not mean much to you. However, let's look at after 2 seconds for an object dropping. 20 meters per second is about 42 miles per hour. That is incredibly fast for something that's only been dropping for 2 seconds, right? Because there's 2.2 miles per hour for every meter per second. After 4 seconds, you're going almost 80 miles an hour. And again, assuming there's no air friction here.